So, Miguel, do you hear me fine?
Hey, Laurent.
Hi.
This is Miguel. We're going to start recording. Is that okay?
Oh, yeah, no, that's fine. Do you
Okay,
hear
then-
me? Okay.
Yeah, we can hear you fine. We're going to mute ourselves, though.
And-
We'll come back if there's any questions from the side.
Okay. You can probably text me if you have a question, and my phone will bing, and they'll tell me to stop.
Okay, I'll give your cell phone number to all the students.
Okay, I will try. That's a good idea. How about the lighting? The lights as bright as this, or can we turn the front just down a little bit?
Mood lighting.
Perfect.
That you completely in the dark, then you're going to be just a shadow.
Yeah.
That's fine with me.
As you can see.
Okay, let's see. This is all, there's too much technology here. Okay, this is my laser pointer. Ooh, does it work? So, we have Gershon Morel from UVic, hi. And then we have a group from Simon Fraser with Dan Gibson right there. And,
Oh, we were right. No, we were right.
and then we have University of Toronto, Lindsay Schonbaum and students.
Hey, Laurent, can you stop sharing your content for a sec so we can see all the other people?
Okay. Oh, the camera's pointing at the back of the head of half the class. Yeah, so. I want to switch camera. Camera select. Wow,
Oh, hey, are we on? Whoa,
That's a big group.
hello.
Okay, so remote sites, you guys are seeing the Queen students now?
No, just us. We can see us. We look great. We look.
Did we lose the call?
What is it?
Hi, everyone.
I can still hear them.
Can you still hear them?
I swear I heard something.
Okay, that wasn't such a good idea then.
I don't know what happened though. I'll drop.
Well, it's the pressure of having.
Of course, it's amazing.
It'll work, guys. Don't worry.
We trust you.
I'll be fine.
Figure time, we just got here.
Oh, they're gone.
Queens.
Queens is gone.
What?
There you go.
Hey.
Okay, we apologize. Something happened at our end.
I don't know if I like this or not.
Okay, so all the remote locations are seeing the Queen students now? Yay!
Hey.
Okay, well, I'll turn back the content now that you've seen our end, and then I'll start talking a little bit about the course logistics and everything else. So let me just, oh dear, camera select, camera 2. Okay. Content sharing. No. Laptop. Okay. All right, so everyone is seeing the content now. It all So what? We're now at 6 locations. This is pretty impressive. Thumbs up for remote locations if you're seeing content. Okay, great. So first of all, Happy New Year, everyone. This is a great start to a new year. We're pushing the envelope of technology and 21st century classroom here. We've been doing this now. This is, I think, the 4th time we've been doing this with different participants across the country. Every time it gets better, but there's still room for improvement. So I just appeal to everyone's indulgence and just be patient, especially the first couple of weeks where we iron out the little bugs. This is a new classroom as well. So all the technology is different than when we did this 2 years ago. Now, there was something else I wanted to say right off the bat, which escapes me now, but we'll come back soon. So this course is being co-taught in 4 different locations: University of Toronto, McGill, Simon Fraser University, and Queen's. And we will rotate the presentations and the instruction in all 4 locations. We will also see other participants joining in through web streaming, such as Christian Morel from UVic. I believe, who else is joining us from a remote location here by himself?
I'm also from UVic, so stay for the room.
Okay. Yes, okay, so let me just move on here. So the format and the course outline, the way it's going to work is, this is an advanced structural geology course. So we expect one to have the basic foundations of structural geology to start off with at the undergraduate level. It's being taught at the advanced sort of 4th year undergraduate level and also graduate level. So we do have graduate students here in the class, but also in remote locations. And the way we've been doing this every 2 years now is we've been doing it with different themes. And this year's theme, we decided to focus on faults and sort of nicknamed the course, the entire course, Anatomy of Fault Zones. And for this, then we decided to bring in experts studying faults at different crustal levels and essentially pool all our resources and our knowledge together so that we can deliver the most complete picture of fault zones from near surface processes all the way to deep crustal processes. Now, so the idea here is to focus on the architecture, the internal workings of a fault zone. So in general, the way we will proceed is work our way from the bottom or deeper processes right here, and then slowly work our way up and finish the lecture and finish the term with near surface processes and active faulting. Now, the intent was to move from bottom up, but because of scheduling conflicts and also our reading weeks in 3 different provinces not matching, we will have to do a little bit of juggling things around, okay? So again, just bear with us. It will work, but it won't be as linear a path from the deep processes to the surface. There'll be a little bit of zigzagging back and forth. Okay. Now, the idea of choosing fault zones for this course is that fault zones are by far probably the most prevalent of localized deformation in pretty much any kind of tectonic setting, whether in extension, in convergence, or even in strike-slip transcurrent systems. And because of their morphology, they operate as good connectors from deep to surface processes. So a couple of ways to answer the question of why we picked fault zones. Well, first of all, they're a very good record of opening and closing of oceanic basins. They also record the rise and fall of mountain belts, and they're amazing plumbing systems for fluid circulation. And when I mean fluid here, fluid is used in the most loose definition of fluids. It could be hydrocarbons, hydrothermal, water, carbon, any kind of gas or fluids will tend to utilize the natural plumbing system that faults make. Okay? And of course, if we have to talk about the society risk of faults, we start talking about the seismic hazard, earthquake hazard. They tend to enhance seismicity in an area. Even old faults don't necessarily die out, so we have the possibility of fault reactivation, seismicity in zones that we consider intraplate and more stable can still bear the hallmark of earthquake activity due to fault reactivation. So again, a good understanding of fault geometry, deformation processes operating in faults are very important for society, for resource potential, and so forth. Okay, so here's the lineup for this term here. So you will be instructed by 5 different instructors. At Queen's, myself, so I will be in charge of the first 4 weeks. Then we'll move to, I believe, McGill. So Yajing Liu. Is Yajing in the classroom right now? There you go, hand raised. So Yajing is a earthquake specialist. So when she will be instructing, she will be focusing a lot more on the geophysics aspects of earthquakes, seismology, and active faults. We'll have Dan Gibson at Simon Fraser. He's a Corlearn Tectonics person, also a geochronologist. So he will provide instruction as to how to date faults, ductile fault zones, ductile shear zones using uranium, thorium, lead geochronology specifically. Christy Rowe, also in McGill, is another earthquake specialist dealing with pseudotachylites, anything to deal with friction-related properties, friction melting, coseismic weakening, and so forth. And then finally, Lindsay Schonenbaum at University of Toronto, and she's our near-surface specialist. Tectonic geomorphology is sort of the discipline that tends to be, or the name utilized to describe this specialty. Also, low-temperature thermochronology, how to date faults at the near surface using isotopic systems that close at very low temperature. So that will be towards the end of term. Okay. So the course is designed as modular. So every 2 weeks, we'll start a new course. That's the idea here. I will take care of the first 2 modules. So we'll start in the very deep process looking at deformation mechanisms, microtectonics, looking at deformation at the thin section scale. And we'll do this essentially for the first 2 blocks. And then we'll move to seismology and fault mechanics. So that's, again, this is the yo-yo I was talking about. We're going to move a little bit more shallowly with Yajing Liu in module 3. And then we'll drop back into the ductile layer or ductile level of fault zones with Dan Gibson to talk about how to date shear zones and ductile fault zones. Finally, the 5th module will be all about fluids, friction, and faulting, and that's with Christy Rowe at McGill. And then we'll finish off with Lindsay Schonenbaum talking about tectonic geomorphology and active faults. Now, each of these modules have a 2-week-long lab attached to it. Okay? So the first week, if I move here, so I know this is a little bit small, but you have that also on your notes on OnCue. So for example, the first block, which is week 1 and week 2, okay, we'll have a 2-hour lecture. Don't worry, we will take breaks. I won't lecture for 2 hours straight. My voice will just break. Followed by a 1-hour tutorial. So that'll be week 1, okay? And the tutorial will essentially introduce the 2-week-long lab. And then on week 2, which is next week, I'll have a 2-hour lecture, and the tutorial is replaced by a 50-minute quiz on the first 2 weeks of lecture and tutorial material, okay? The quiz is really just to keep everyone moving forward and making sure, all the concepts, the key elements are being assimilated correctly. Then we'll move to the second block, which will deal with flow, rotation, and bigger scale orogenic processes in weeks 3 and 4. And there's one lab attached to that on vorticity analysis and crystallographic preferred orientation. And then finally, the last 2 weeks of before reading break, or at least the Queen's reading break, then we'll deal with fault mechanics and seismology. And then we have our reading break, and then we return back with Dan Gibson, Christy Rowe, and Lindsay Schommenbaum. Okay? We haven't figured out exactly how we're going to deal with McGill's reading week, which is, I believe, the week before Queen's, and Simon Fraser, which is the week after, or vice versa, I can't remember. We do have live streaming on the web as well. So as the week progresses and we get all the technology sorted out, you guys will be provided also with a web link that you can join if, for example, there's a snowstorm, you can't come in, you're sick, or you're on reading week on the beach in Bermuda or whatever, and you want to join in and don't miss a lecture. That's the idea. Okay? All right, the marking scheme is also different to many courses here at Queen's. First good news, there's no final exams here. Okay? There's no midterms either. The bulk of the work are the 6 lab assignments, okay, which are lab reports. They're not just little 2-page lab assignments. We will talk about that in the tutorial, but these are full-fledged lab reports that have to be presented in a professional manner. So there's 6 of them, and they're worth 75% of the mark if you're registered in the undergraduate course in 481. The 6 quizzes are worth 25%. Okay, and again, they should not be too difficult for you if you've attended the lecture and followed up on the material, and that will comprise the 100% of your mark right here. Now, for the graduate students, the marking or the breakdown is a little bit different. What's added is a seminar presentation. And for you guys, and I will talk to you separately later on this week, but you will each pick a theme, a structural geology theme, and then later in the term, towards the end of term, you will be in charge of a 10-15-minute presentation, mini lecture to the other graduate students. And that's done just between the graduate students. The undergraduate students won't participate in this unless you really want to listen to what the graduate students have to say. But essentially the idea with these seminar presentations is learning by teaching. So we will make a list of possible topics for you guys, and then you will go and do the work, prepare a 15-minute lecture, and teach us towards the end of term on that specific theme. Okay? The lectures will always be in this time slot, 1:30 to 3:30, and then we'll move. How we move from the lecture to the tutorial, either we take a 10-minute break and finish early, or we take an hour break and come back at 4:30. I prefer doing sort of a 10-15-minute break each 50 minutes or so. That way we can all be done by 4:30 instead of lingering here until 5:30, if that's fine with everyone, including the remote locations.
Yeah, we'd prefer to be done by 4:30.
That's what I thought. Perfect. Okay, so we're on the same page here. Now, we do not have set textbooks for this course because, again, each 2 years we teach very different material. Although I did list a couple of here that I know are in the library here. We also have online access to some of these at Queen's. Earth Structure here is our introduction or our 3rd-year structural geology textbook. Any introductory structural textbook would do quite well to refresh your memory of key concepts. Microtectonics is a textbook that I will use the first 4 weeks, quite intensely. A lot of figures are coming out of that textbook. It's available online through the Queen's Library, I know here. I don't know about McGill, Simon Fraser, or U of T, but this is a good textbook to have, in fact, because it's got a lot of really neat things in it. Tectonic Geomorphology is a textbook that will mostly be utilized in the last 2 weeks of class during Lindsay Schonbaum's lectures on tectonic geomorphology. And Mechanics of Earthquakes and Faulting, this is a book by Chris Schultz, could be a good resource also when we're dealing more with the brittle regime of fault zones and the seismogenic zone. As well, we will constantly provide key references and key readings in the scientific literature. So these are journal manuscripts available through the library. We're going to get you to read scientific literature a little bit more. It's a good skill to develop. If you haven't read articles before, and you'll start doing this in this course. And it's a good way to just keep abreast of the latest and the greatest out there. Okay, so none of these textbooks are mandatory, but they're highly recommended to go and grab and key information if you have any questions. Okay. Now, the Queen students are familiar with this, perhaps not the other classes and the other campuses. At Queen's here, we use an on-cue system to archive all our lecture notes. The system is up and running now. Hopefully everyone got access to it as of midnight last night, I think. Hopefully the remote students as well got access to it. On this, we will have the lecture notes, the tutorials, the lab assignments. Any extra information will be posted there as well. One thing that I forgot to do this morning, this afternoon, sorry, but we will also podcast our lectures and repost that on OnCue. So if you, especially for the remote locations, if you want to go back, some of the graphics were not nice enough or my voice broke down, you can always go back and listen to parts of the lecture. Or if you have a hard time falling asleep at night and you want to, yeah. Okay, so that's how we're going to set it up. At the same time, each one of you has a Queen's email. For the Queen students, that's pretty obvious. But for the other remote participants, you've been given a Queen's email address for the term. And this will be used whenever we have communication to send to everyone. So it's very important for you to make sure to monitor that Queen's email address, because any email traffic related to this course will be sent automatically to those Queen's email address. The best way is just to have a forward command of those emails to the regular email address that you monitor on a daily basis. Any questions so far on the format and sort of the, yes?
PDAC, what are we going to do for that?
Sorry, but I'm lecturing. Okay, if you want to break for PDAC, I mean, that's extracurricular. We'll have to just continue lecturing, and then you'll have to find solutions for your extracurricular. Unfortunately, there's too many people, too many campuses to take a break for going for a fun time at PDAC. Sorry, job hunting. Okay. Any other questions from other remote locations? You guys hear me fine? You see the graphics fine? It's all good? Okay, so I'm not hearing anything from remote sites, or you guys tell me if they start waving, and mad panic. I can't see them. I'm looking at you guys. Okay, so what I want to do now is actually start lecturing. So one thing, though, I will ask you guys at Queen's to watch the time, and I'm be looking at your eyelids, and if I start seeing you going, sort of lower and lower, and the eyes are dimming down, that will give me a clue that it's time for me to take a break, okay? Also, we don't want to, we want to take a reasonable break every 50 minutes or so. So just throw something soft at me, okay? Or just yell or something, okay? Okay, so my arm's gonna be really tired.
We lost one from UA.
I
There's a
think you
Russian.
just turned her camera off.
Yeah,
Okay.
so I think Kirsten just turned the
Okay.
camera off.
That's why.
Okay. Yeah. All right. So what I wanted to do today, and this is typical of my first lecture in this kind of course here, not knowing if technology is going to fall apart or not. So I planned a little review for strain analysis and microtectonics. Now, for some of you, especially those of you who've taken my structural geology course just before Christmas, this should be a piece of cake. Okay, this should be just a review of the last couple of weeks, or the first couple of weeks of last term. If not, it's just a friendly reminder, refresher of key concepts dealing with strain, and then we'll move towards shear zones, mylonites, shear sense indicators, and deformation mechanisms. So what I will do now until we finish today is really focus on the ductile regime and things to that we can look for and that we can utilize to better understand the ductile processes in ductile fault zones at depth. Okay? So let's start with very, very basic definitions here of deformation and strain. So simply put, deformation is a very, very general term that essentially defines four components of objects undergoing change. So translation, rotation are elements of deformation that doesn't imply any internal change. So plate tectonics, for example, the Indian continent moving northward is undergoing translation, and during that translation, the Indian plate is in fact deforming. The same way as a car driving down the 401 highway from Kingston to Toronto or towards McGill is translating, it is deforming, but hopefully not straining. Okay? Now, when we talk about rigid body deformation, rotation and translation are key components of deformation. We will be a little bit more specific when we talk about strain. Strain refers to internal deformation, internal change of state of this original grid cell that we have right here. Okay? So dilation, either negative or positive dilation, contraction, dilation, the cell width or the line length between the original object and this state right here, the lines have changed length, either increased or decreased. And that refers to dilation. When we talk about distortion, which is this state here, what changes are the internal angles. Okay? So strain, which is a little bit more specific than deformation, refers to change in line length and or change in angles internally. You'll notice that rotation, for example, there is a change in angle, but it's with respect to an external reference frame. But internally, it's rigid, so that's why we call it rigid body deformation. All right. The other two very important concepts to make sure we understand are the concept of homogeneous versus inhomogeneous strain. If we want to do strain analysis, which we will do in the first two labs of this course, we have to invoke homogeneous strain. Okay? So what do we refer to as key elements defining homogeneous strain? Well, planar surfaces before strain have to stay planar after strain. Lines that were initially parallel before have to stay parallel after. And straight lines before strain have to stay straight after that deformation event. Okay? Very quickly, if we utilize these criteria for homogeneous strain, we'll come to realize that nature is by definition inhomogeneous. We take even the simplest fold shape, like this one here in the lower left corner. A fold shape is by definition inhomogeneous, especially in the hinge zone, where lines are not straight anymore, and we may even have a deviation from lines that were initially parallel. And in third dimension, the planar surface is not planar anymore, especially in the hinge zone. Okay? So if we're trying to do strain analysis on a folded surface, we have to break it down into separate, smaller components to satisfy the homogeneous conditions. In this case here, we could focus our attention on the left limb and the right limb, which individually satisfy the homogeneous criteria. And then in the inhomogeneous zone right here in the hinge zone, the simplest thing to do there is to break it down in smaller and smaller pieces or surfaces or volumes if you're in 3D until you satisfy those three conditions here. Until those are satisfied, however, you cannot perform strain analysis. Okay. Okay, now, again, these are concepts from the Introduction to Structural Geology textbook. When we talk about line length change now, there are two quantitative values that we will utilize. Okay? Extension or stretch. Usually the E value or the S value, which is a numerical value based on finite length versus the original length. So it does assume that you know the original length of that specific line and the final length that you can measure. In the case of, let's say, a deformed brack, we could take the hinge line right here. We have an original length of 3 centimeters. The deformed length has extended to 5 centimeters. Then the ratio of the final length over the original length would define the stretch. Okay? If we do the final length minus the original length over the original, that is what we call the extension value. So you can use one or the other. And of course, we could apply that at the brachipode scale or even at the cross-section scale in the lower right. When we talk about angles now, we will talk about two other values. One is the angular shear value, and the other one is the shear strain value. Now, for the angular shear, what the key here is to initially define two lines that were initially perpendicular before strain. Okay? So if we take this example right here, and we have two lines, line AF and BF, which are deformed now. Oops. Do that again. Line AF at one point pre-strain was perpendicular to line BF, and there's an angular change of that line of 30 degrees clockwise, which will be clockwise positive value. So in this case here, there's an angular shear of 30 degrees in the BF line direction. Okay, so the line initially perpendicular to BF, AF, has been rotated clockwise by 30 degrees. Okay, so it's an angular value. There's probably a better way of defining that change, and that's using the shear strain value. And the shear strain value is, let's say we have an object of 1 by 1, two orthogonal lines, of equal length. Okay. If we talk about a shear strain value of 1, that essentially represents, so let's draw this line right here. This is the original line here. This point here, okay, has shifted by 1 unit cell. Okay, to the right, positive, and that would be a shear strain of 1 in a dextral sense. And this is shear strain in the x direction. Okay. A value of 2 shear strain, this case here, this point here now has shifted 2 unit length parallel to the x direction. So that would be a shear strain of 2. To give you some example, in some shear zones, for example, the South Alpine Fault that you guys will be working on during your first week, your first lab assignment, there's been some shear strain values reported in the hundreds in that along the Alpine Fault system. Okay? Which means the greater the shear strain value, the more offset the shear zone accommodates. Okay? Because it's a ratio of the width of the shear zone versus the lateral displacement, the displacement in that fault zone itself. Okay, so the greater the value, the greater offset of that fault zone. Okay. All right. As folks at Queen's are now very familiar with one of my key sentences or key lines I keep repeating throughout the term, for strain analysis, or for any kind of structural analysis that you're doing, the strain ellipse is your friend, okay? A good understanding of the strain ellipse can go a long way to interpret and understand deformation systems, okay? So if we take a undeformed circle and we deform it, or we strain it, let's be specific here, we strain it, therefore we're either changing the volume or distorting the shape of that circle, will automatically produce an ellipse. The ellipse will have a long axis and a short axis. And then there will be a series of intermediate lines in different orientations. Okay? But there will be 2 lines, one which will be the longest and one will be the shortest. Okay, so let me draw this in green. The longest in this case here will be this line right there, and the shortest, so happen, will be perpendicular to that one. Okay, the longest is the line that has accommodated the most stretch. We will refer to that as the S1 direction. The shortest will be the S3, okay? The minimum amount of stretch, or conversely, the maximum amount of shortening. And that's the S3 value, okay? Now, in that strain ellipse, we will have these 2 directions, the S1 and the S3, and then we'll have 2 lines that will have 0 stretch value. Okay, which are these 2 lines right here. Okay, the stretch equals 1, meaning final length equals the original length. These 2 lines define strain quadrant boundaries. So anything in this gray zone here, all the lines in this orientation will have a positive stretch, and any line in the orientation within the black zone will have an element of shortening. Okay, so these are the 2 components, stretch and shortening, and the boundaries of that are lines of 0 stretch, and that defines the 4 strain quadrants of our strain ellipse. 2 stretching quadrants and 2 shortening quadrants. Okay. All right, more key definitions here before we go too far. Now that we've introduced the strain ellipse, let's talk about flow path of strain. And there are two end members here that we'll talk about, pure shear versus simple shear. So for this, we introduced the concept of progressive deformation. So in stage 0, at time 0, we start with a circle, and then this is time 1, time 2, time 3. You'll notice that for each increment in the top panel right here, okay, the circle gets progressively flattened. There's absolutely no change in angles of the two maximum and minimum stretching lines, although they're getting shorter and shorter or getting longer and longer, okay? In this case here, we refer to strain as progressing in a coaxial manner, okay? So the lines here, maximum and minimum stretch, always stay in the same orientation. They just change length in progressive deformation. And this is what we refer to as pure shear or coaxial. Conversely, simple shear is the case where, as we progress in time 1, time 2, time 3 increment, the lines of maximum and minimum stretch rotate through time. And they also change length through time. So in this case here, strain is accumulated in a non-coaxial way. There's a rotational component to the strain, okay? And that's what we refer to as simple shear. These are end members, meaning that in between this and this, there's a whole range of deformation path that you could have. You could have simple shear with a little bit of flattening at the same time, so that the shear zone width, which is, let's say, this line here, with time narrows. Okay, so the strain ellipse will rotate and will also flatten as well. So this will be general non-coaxial flow, where there's a component of pure shear and a component of simple shear operating at the same time. Okay. Now, this brings me to the introduction of instantaneous versus finite strain. Okay. So we do have to think about this. If we're dealing, let's say, with pure shear, as we progress deformation in pure shear, we'll be incrementally adding strain. Now, I like to use the analogy here of just a good old Friday night party, where one beer is one increment of strain, okay? If you arrive at the start of the party, you have your first beer, first increment of strain will equal that first beer, okay? If you add the second beer, that beer is the same increment of strain, but cumulatively, right, your strain is that much higher because you've added 2 beers to your system. Your buddy that shows up late, right, while you're having your third beer, okay, will have his first beer. So incrementally, his strain will be a lot less than yours, although the incremental strain is the same, the finite strain will be different, just because one joined the party later. Rocks behave the same way, surprising, okay? So in this case here, by time 4, okay, this increment of strain, or this finite time strain, is the sum of 4 identical instantaneous strain components, okay? So this is an example in pure shear. And you'll notice that the incremental or instantaneous strain, the upper row, and the finite strain, although the ellipses are of different length, the angles of the instantaneous strain axes and the orientation of the finite strain axes are parallel. Okay? There's no angular difference between instantaneous and finite strain axes. Let's look at it now with simple shear. Okay, and in simple shear, of course, we're going to do, let's say, this case here where it's a dextral shear sense. The instantaneous strain at that first increment of dextral shear, if we put a circle in a deck of cards and we shear it by the smallest of shear strain, will produce a strain ellipse that will have an instantaneous stretching axis lying at 45 degrees to the shear zone boundary. Okay? That defines our instantaneous strain ellipse. Of course, at time increment 1, the finite strain will equal the instantaneous strain. Okay? Again, this is the value of my beer. Okay? This is the sum of 2 beers in simple shear. You'll notice as I move forward, each increment of strain, each beer is the same volume of alcohol, right? But cumulatively, the object is adding all those increments into a finite strain state that is the sum of all these different increments. Readily, what we can see in the final stage, in stage 4 here, the instantaneous maximum and minimum stretching directions are very different than the finite instantaneous, finite maximum and minimum stretching direction. Okay? So in simple shear, this here is the rotational component of strain. That makes a huge difference with pure shear. Okay? The finite stretching directions rotate away from the instantaneous. That's the definition of what we call vorticity. Okay? I'll get better with my handwriting, trust me. Okay? All right, now this seems very theoretical, but I want to give you a very specific example in the nature where we can actually track this instantaneous versus finite strain. Okay? So here's an example of dilational quartz veins, okay, in a shear zone. Now, keeping in mind that these quartz veins, let's just take this one here, has a sigmoidal shape. Okay? It's essentially a crack in the system being filled by hydrothermal fluids. Okay? The youngest part of the crack is at the tip. That's where the crack is propagating. So if I were to draw this at the next increment of deformation, okay, this crack here will propagate further in this direction. Okay? And it's dilational, meaning that there's extension operating in this direction here. So the shortening direction is like this. The stretching direction is like this. So that would be my S1, and that would be my S3. This would be an instantaneous strain ellipse. Okay. Now I'm going to show a video. I don't know how it's going to work out with the remote locations. It might be a little bit grainy, but you should be able to grasp the concept here. That failed miserably. Bear with me. First day with new technology here. This is just not working.
It's moving now.
Is it moving?
Oh, yeah.
Oh, interesting. I'm looking at my screen and it's not moving.
Yep.
There you go. Okay, so while this plays in a loop, okay, what I want you to look at is this component right here, in the middle of the dilational vein, okay? So initially the crack, and I'll use different colors here, okay, at time 1, okay, the crack will be oriented this way here, okay? Responding to dilation in this direction, stretching in this direction here, okay? At time 2, and I'll just draw time 2 here, okay? Instantaneously, the crack is still cracking in this direction, responding to the instantaneous strain this way. But the core of the vein that was formed at time 1 is now passive and is undergoing the rotational component of flow. And this being a dextral shear, the core of this will rotate clockwise. Okay. Okay, so the yellow component is the time 1, the green component is the time 2. So in the single finite object you see in the rock, there are different components of instantaneous and finite strain that you can see here. So there are components here that you can in fact interpret the sense of vorticity of the flow, the rotation of the finite strain axes away from the instantaneous. So as long as you can document this rotation, you've defined yourself a shear sense indicator. Hopefully that's clear. Okay. So, when we talk about material lines now in flow, whether in pure shear and simple shear, lines will change length and or change orientation, depending on the flow type. And here's a diagram where we have on the left here pure shear and simple shear. And we start off with essentially a bicycle wheel with an infinite number of lines of equal length at different orientations. Okay? There will be lines with zero rotation, zero angular velocity. Okay? In pure shear, there will be two lines that will never rotate, okay? Which are these ones right here. In simple shear, conversely, there's really only one line that will never rotate, and it's this line right here, which is a line parallel to the shear zone boundary. Lines that never change length, however, in both systems, there are two such lines. Now you'll notice that in pure shear, these orientations are the lines of zero angular rotation, but the lines of zero change of length, which are these lines that define the strain boundaries, the strain quadrant boundaries, okay, are right here, okay? They won't change length, but no, it's up to you to cancel the call. Okay, that was quick.
Greg's over.
Sorry, guys, we had a technical mishap on our end, but it happened 50 minutes at the start since the start of my lecture, so I suggested maybe taking a 10-minute break, and then we'll resume again if that works.
Break.
Yeah? Okay. That way I'll reorganize my notes here.
Sweet.
Cool. All right. 10
There
minutes.
are more kids in this one than there are all of the others.
Yeah, you go back down the hallway.
Actually, so most of those McGill students are grad students, actually.
I think everyone else is grad.
Yeah, no, because I went to a conference in October, and I went out drinking with those two girls in red and the guy behind them. So, so as far as I know, all the McGill students are grad students, and then I'm assuming all the others are. I think I'm the only Queen's grad student, yeah. No one at this freaking university does any work in structural geology. Yeah, there's like me, Zoe, Heno, and Sienna.
Yeah,
And that's like the four students who, like four of us who work with Heno. It's like with Laurent, and like no one else cares about structure. It's kind of frustrating. But whatever, that's a...
You got all of us.
This is true. This is true. So it's actually pretty sweet seeing so many third years in here. This is... That's sweet.
Unfortunately, we have a bunch more men. But to take it, if you're again, you have to basically drop to. Are you taking drop 100%? You have to drop geophysics.
Yeah.
And it interferes with another one of our lectures. Like I'm missing a lecture right now.
Yeah. Okay.
So like everyone's going to that.
Yeah.
And I technically would be missing two if I had that's my previous the other.
Yeah.
Because those lab also so like there's a bunch of like geophysics.
Yeah.
We're also but
Yeah, but they just, so we're missing all the third year angels who might be.
There's two of us, it's me and Laura.
Okay.
It's only a half course, I know.
Yeah, so
Yeah.
that was what I was emotional. Yeah.
You went to my
You have to.
I absolutely 100% will.
Actually, really
Are you going to Bermuda?
Well, they heard me when this happened, so like,
this is really different.
Yeah.
every single construction.
My last course in this course, which is going down.
Well, if you get the believe me, I used to catch the bus. I used to take the bus when I lived here. I used to come back for hours. I was on West.
As you
But you have to do it. You can't miss the bus. That's the thing. There's a bus that leaves at 18 every hour at like 15. Like here and there. Okay. So like they'll basically pass each other on the way. So like you can get there. If you catch those ones, you'll be able to make it like 5 minutes. That's not bad at all. It's actually quicker. It's honestly quicker. It's quicker for me to take the bus to West than it is for me to walk. I live like. I never realized that. So I liked here, and I was like, the bus.
That example, I was like, I walked over and I'm like, okay.
Well, yeah,
If you just reason, run a stop the bus stop, 20, 15, go early for like 15 to 20 and go catch the bus. The 1, 2, 7, 8, yeah. Or the just anyone
Content that you're writing was.
you guys were 30.
So like,
His brother is like, I don't know.
they're 70. And I just like, I got
So the lab is on 10
classes like, I got a 65. I got a 60.
It's probably close.
Like, I'm really good at it.
You guys are
Yeah.
I don't know.
So.
Sorry?
I don't even see close to 30 people.
And I'm not even, like, a lot of flights got
And you're not even registered yet.
A lot of flights got delayed. Like,
Yeah.
so the shooting, in Fort Lauderdale, the shooting, a lot of people were delayed.
Down there.
I had like 3 friends in Florida, and then a lot of flights got
Oh, people
California.
look live, right? That's what you see.
I don't know, a lot of flights were delayed.
What's better to do than study structures?
Like,
Look, I know, I brought my notes. I know even,
You know, a friend of mine, I think, is still in the middle Middle East, so.
Like Toronto was on high watch.
Oh, have you seen? Oh wait, did you check your
I think you have one. You have one.
Cheap ass.
Oh, I understand. I want to
Yeah,
show
in
her.
order to get the grade, I had to get the grade. She's like, why can't we just?
Yeah. Of course you know.
You both did math. You're both. You both
I
did math.
complimented that.
But they told me both.
Yeah, like
It's literally the exact same thing. You both didn't ask for it. Basically, yeah.
And then all of a sudden I like highly decent mark.
But I'll be coming back here.
I do too.
Flagship.
I think yeah.
Are you laughing at me?
Maybe if you went like switch to different people, like when they switch to
Well, no, now I'm getting trained in that.
because then
Like snap your finger.
Exact same.
No, I remember like,
Really, people who live in there forever just do crap.
they didn't even know the like,
my
your piece how you just say it, like different mics, like snow.
Literally right here.
Well, not even that, just like the fact that like anywhere in this room you could be.
Yes.
We always talk like quietly, but like very quietly.
Well, yeah,
Just, like, over when it's going on.
Yeah.
And it's like undoing that other people might be hearing it.
No, it's subsidized.
Yeah.
But like,
It's kind of like it's actually, it happens to be less.
I'm like intrigued to see how the other classrooms organize it.
Yeah.
Because like
We have like a 3 camera setup here.
yeah, and like look at the top right.
Yeah.
Zealand told me he had
So like, I don't actually know what they're seeing, because they might only be seeing the PowerPoints and hearing us.
No, they're saying that.
is like.
Yeah. That's what I'm pretty sure that's what they're saying.
think I
see that, yeah.
Okay.
They had a GoFundMe, so why don't you GoFundMe?
Then I don't know.
Yeah, so
Maybe they'll set up more cameras.
Possibly, yeah.
Or we just gotta struggle to before.
so yeah, like my.
That call might have been
Like
from the other
on
person.
the top right, like,
Maybe
right.
Yeah, like it just doesn't hold his like, so it's just like whiteboard.
Friends live in.
There was one thing on the corner that indicated there was somebody else still there.
Maybe
That
we
could be-
they only saw the.
So I think that might have been, that might have
Right?
been the fault.
Like that.
Only from the PowerPoint?
That could be.
Like,
I was thinking,
not
how
very
they
close to
see
like
it
summer.
like that.
I knew she was there because like the,
It's not great.
like it was like no microphone, or just like one person that wasn't, that didn't have the camera on.
Yeah, 'cause like,
Where you had
But
I think it was Christy mentioned
Not
like
sure.
you gotta like share your content.
Yeah.
So I assume that meant like share the PowerPoint.
month after.
Yeah, I'm assuming they're just seeing
So but just like whatever's on that screen is what there's he will have.
There's fun desks.
Yeah. Where's that?
So they're just like.
That's Miguel.
Very nice.
Because we're not Miguel.
Because we're cheating. No, I'm not taking it to the next year.
Those are fun equipment.
You know, I do, but I
That's the relief.
So,
do, but
Really nice stuff.
Geophysics.
but I also need to like have my hands properly.
I remember there were a lot of people.
Yo, we got that new stuff. I was having such a
Why?
What was the
Gary Kubiak. Well, you spent time off.
Last semester, and then I dropped it on. I finished my exam. Yeah, and the next exam was the back down. But Picothermos falls out. She just like that was like a real lump. That was just like cracked in half. And I was like, does it matter?
I know. I was hyped. I was hyped thinking it up. I was like, whoa. I must have done one. I had to get it.
Lab is 2:30s to 4:30s.
I went like, you know,
You basically got your
still. I knew I do 75% of the exam.
They're nighttime.
Yeah, but that was
As long as I can get that.
I remember, the guy at the end, because like, when I finished, I looked at yours, and I looked at mine, and I was like, okay, you remember your own paper, and I was like, dog, it's like 5 minutes till the exam's done. Look at this, I've been drawing for like an hour, like, I'm not changing it now. What am I gonna do now? Yeah, it was funny.
3-hour clocks.
One for an hour.
It's set up so I don't have
I know it. That was a fun exam. I had a good time writing it.
So I have like 1 3-hour lecture and maybe like
He's moving fast, because he wants to put it down.
Yeah.
I was gonna.
It's still gonna crash.
It'd be nice to get a surface
Actually, yeah.
iPad.
Yeah.
Because the iPad is like,
Oh no.
And like, ask Connor to save it.
Don't get.
Just master. It's that arm's gotta get tired holding that thing up for just a caramel one.
I tried to do that last time.
That's what I did.
And I dropped it.
Through the-
Yeah, I did it last semester.
No, that's for the
Because I had geophys, which
Oh, it is
was
a
4 classes started. And I had 6 courses during the semester. But by the grace of God, it worked out. And I know. I worked.
Yeah, they do that.
My arm's going dead, so I need something.
Yeah, the captain.
When I was in Nepal with him, I was with my co-supervisor who also, well, he's Romanian, but he speaks French better than he speaks English. And then like the Nepali crew that we had, like most of them, like they're all Nepali, they all speak French better than they speak English because they like Nepali in like a French.
None of this.
Yeah, like they target all the stuff towards French people, right? So like, I mean, I can speak French. It's not amazing, but I can.
you can like fast.
I can get through. It's not great, whatever, right? But like, you know, it's like the majority of like all the geology is always in English, but like around camp, like you know,
table light about that.
evening, like setting up camp.
Do all Laurent's grad students? I would go crazy.
Dangerous.
Again,
I
this
think
is
it's
it's
so.
just trying to figure things out.
I don't think so.
Do you need something to prop that leg a little
Me
bit?
and Hano,
There.
and I think
I'll sacrifice the book,
But
just prop that up a little bit more.
Well, we don't do that.
I just don't want
It's
to,
holding, but
yeah.
yeah, I just don't want to fall, I
But yeah,
just want to fall and wreck your
geology,
computer.
sometimes like.
Yeah, it looks like the leg's a little short.
I'm just like.
Totally. Except in geology when I have no idea how to do any geology in French. I
Work pretty
just don't
good.
know any of the terms.
They go up.
Yeah, like, the geology terms that are already French. That's about
Oh, it's frustrating. My favorite type.
Yeah, you have to.
I really hope that we're muted.
Probably not.
I don't have much. I need to. I think so. I think
Yeah, like, yeah, like,
You don't need this, right?
my brother's.
Summer class started chatting.
You didn't get to say anything.
Are you kidding?
Yeah, like the whole.
Ladies and gentlemen, the future of technology.
Yeah, this is Queen's technology at its Throw that in. That's gonna
Meanwhile.
Oh, okay.
Oh, that's funny.
Ooh,
Still
I
never
made a
ordered
pizza for
pizza.
I remember.
That's cool. No, I haven't.
As soon as someone says
You're just like, well.
I think it makes so long.
Is everyone back?
I think they're missing Mark.
just go.
Miguel, U of T, Simon Fraser, UVic, you guys are all there? You hear me fine?
Hey, we're back.
Okay, great. Okay, well, sounds like everything's working well. I won't jinx it too much. Renault's on the lookout for any incoming calls that might disturb our lecture, but hopefully that should be resolved. So I just moved forward a couple of slides for the second hour here, because I do want to move to some new material and less so review the introductory basic concept that everyone should know about. Now I want to move into shear zones. So essentially the ductile component, the deeper parts of fault systems, and then slowly zoom into the microtectonics and the type of deformation mechanisms, and most importantly, the type of textures that we can recognize in thin section that enables us then to interpret environmental conditions for faulting. And those are, we're talking mostly temperature, the degree of strain, and so forth. Okay, so I'll start with shear zones, and then we'll move slowly at smaller scales towards shear sense indicators and towards micro-textural features that we can then go forward with our shear zone analysis. Okay? So first of all, when we talk about shear zones here in this, and certainly when I talk about shear zones, I'm talking about the ductile component of fault systems. So many people, when describing faults, or if they talk about faults, they will talk about the non-cohesive type of deformation that breaks and ruptures the rock. Okay, that's more of the brittle component of a fault system. If you're talking about the deeper parts, the ductile component of a fault system where deformation and rocks strain while maintaining cohesion, this is where we talk about shear zones. Okay, so there's no break in cohesion, and right away, and right at the top of my slide here, when we talk about shear zones, we're actually talking about a manifestation of heterogeneous deformation. Now, you might say right away that, by saying that, that means we cannot do strain analysis, we pack our bags, we go home. Because one of my first slides today was, well, to do any kind of strain analysis, we have to talk about homogeneous strain. Shear zones at a map scale, at a continental scale, or even at a thin section scale, is a pattern of heterogeneous deformation. So if we take this map right here, all the black lines here are in fact ductile shear zones in the Archean greenstone belt of northern Quebec and northern Ontario, in the Abitibi belt. At the map scale right here, these lines here are manifestation of heterogeneous strain. The strain is very, very different if you're within the black line here than if you're in the green or the pink component of the map. Okay? The same goes for this little sketch on the lower, in the left part of the slide. And this is just a schematic diagram showing form lines or bedding. And then when you get into the zone between the two dashed orange lines, there's an element or a component there of more intense distortion. Okay? So the strain within this zone here compared to outside is very different. So the strain at the entire map scale here is heterogeneous. However, if we go inside the zone right here, whether we're here or here or here, the strain is homogeneous within the shear zone. Okay? The same thing if we're at this map scale here and we would walk along and inside and have a look at inside the black lines within the shear zone, we'll assume homogeneous shear strain inside that single shear zone. Okay? So essentially now when we talk about shear zones, we have to define what we mean by shear zones. These are planar zones of concentrated shear strain, okay, that accommodates displacement. okay? And it operates and deforms the rock in a cohesive manner, so there's no loss of cohesion. And just like in rivers, for example, the highest strain, the highest displacement rates will most commonly occur in the central part of the shear zone, meaning that if you go from the edges of the shear zone towards the core, there will be a strain gradient, where strain will increase in intensity towards the central part of the shear zone, or will decrease as you move away from the shear zone center towards the shear zone boundaries. So to properly define what a shear zone is, it's essentially a planar zone of localized strain, and let's be specific here, of localized shear strain. So I should probably add here shear strain, okay, and in which we can identify, at least qualitatively, a strain gradient going from the edges of the shear zone towards the core of the shear zone. So to recognize a shear zone in a map pattern, you need those two conditions. You need to document a localized zone of shear strain and also the presence of a strain gradient going from low strain towards very high shear strain in the center. Okay? This displacement is producing a rotational component to the strain. Okay, so shear zones will behave or will record a dominant simple shear flow path. Okay, so a strong tendency towards non-coaxial deformation, and all of this to accommodate lateral displacement. And I've put these two images just to illustrate these concepts. This is a diagram, a field notebook diagram of Ben Peach. Now, those of you familiar with my lectures, I always bring back some historical characters that have really made landmark contributions to structural geology. Ben Peach was one of the guys leading the Scottish mapping project in northern Scotland along the Moine Thrust fault, the Moine Thrust, and that group of geologists really produced the first rigorous documentation of a shear zone in the Moine Thrust in northern Scotland. And this is a road cut diagram of the thrust system, and you can see clearly on this diagram here that you have zones of higher strain, lower strain, higher strain, lower strain. At thin section scale, this diagram would look a little bit like crenellation cleavage. Right? These zones here, where everything is planar, are zones of localized strain with a marked strain gradient that increases from the wall walk inside the shear zone. Okay? So these zones here, and there's probably 5 or 7 of them on this diagram alone here, are really following this definition of a shear zone, localized strain and strain gradient documented. Right? And these are diagrams that were produced, in the 1900s. This map here is a map of New Zealand, and in this case here, what's being portrayed in the color code here are shear strain rate. Okay, so this is measured using GPS data in particular, and you can see clearly the plate boundary following this zone here with the maximum shear strain rate, so this is maximum displacement per time, being localized right at the core of this plate boundary that's called the South Alpine Fault, which will be the topic of your first lab in this course. Okay, so just this color coding going from blue to green to red marks a strain gradient. And if you were to do from a very schematic perspective here, draw the shear zone boundaries, right? One, you could kind of draw this like this. The strain gradient, and this is very important, the strain gradient, trying to find a color that would show well, is usually perpendicular to the shear zone boundaries.
Hey, Laurent, what are the units of shear strain there?
Okay, so shear strain is a unitless value because it marks just a, if you remember my first slides in the first half of the lecture, shear strain is just a measure of lateral relative displacement versus along an axis. So the ppm here, I'm not quite sure what that refers to. It's really over time, which is the rate of displacement. ppm, it's not parts per million. I'll look that up. I can't remember, quite honestly. But it really marks the rotation component over time measured along the Alpine Fault. Okay. So here in this case here, the strain gradient is perpendicular to the shear zone boundary. And if I were to draw the shear zone boundary on the bent peach diagram here, the shear zone boundary is like this. The strain gradient, again in this case, is increasing towards the central part of the shear zone, and the strain gradient is perpendicular to the shear zone boundary. Okay. So probably the first question we should ask ourselves, because shear zones are occurring in pretty much every continent, in any kind of tectonic environment, is why is strain localized in the first place, as opposed to be homogeneously distributed at the map scale or at the thin section scale? So there must be one or several reasons to localize strain in a specific zone and not everywhere the same way. Okay? And the list goes on. I've just put 4 here, but there's actually quite a lot more. One, we could invoke grain size reduction. So for example, if we're dealing with a granite or even a sedimentary rock with variation in crystal size or grain size in that sedimentary rock or igneous rock itself, grain size will be a great influencer in strain localization. The finer grain material will tend to activate ductile processes a lot more so. And we'll talk about these processes like dislocation and diffusion in a couple of slides. But grain size differences, especially the finer grain component, tends to promote localization of strain. Okay? We could have already in our rock preferred crystallographic orientations, which will favor intracrystalline slip. We call those dislocations. So if we have an already established part of our rock with a preferred orientation favoring intracrystalline slip, that could initiate strain localization, and then once it's localized, then more slip will just further localize strain and so forth. Okay? We could be dealing with a massive rock with, for example, some kind of reaction softening. Metamorphic reactions, or in this case fluid-related sophening, hydration of certain metamorphic minerals, think of serpentine for example, with fluids percolating in ultramafic rocks, initiating metamorphic reactions and hydrothermal reactions, we could produce a weaker rock that will then accommodate and localize strain much more. Okay? Another component here that could be important, and this goes under geometric softening, is if we have a fault already existent there in the first place. Reactivation of fault, so there's a fault already there, there's already preferred orientation of micas, for example, that could in turn favor more strain localization. Okay. Now, in the ductile world, probably one of the most important mechanism to localize strain is melting. Now this diagram here comes from a series of experiments. This is a diagram out of Rosenberg and Handy, a paper that was published in 2005. And it's very interesting here. The two axes here, the x-axis is the melt fraction, and this was conducted experimentally, okay? 0 would be an aggregate with absolutely 0 melt, and then 1 is a rock that has undergone 100% melt, okay? And the blue line here is the strength line. So of course, a rock that has 0 melt is very strong. A rock that has 100% melt is virtually has no strength to it at all, okay? So what's important to see here is that there's several breaks in slope on this strength curve, okay? So here's a rock with 0% melt. This point right here represents a rock with about 7% melt. Now this point here at 7% melt compared to a rock with 0% melt is incredibly weak. Okay, so it doesn't take much. Okay, so essentially by 8% melt, a rock is literally as weak as a rock with 50% melt in it. Okay, 50% melt would be just about right here. So the gray zone in these diagrams represent sort of the visual melt component of that rock. So a rock that's got about 8% would look something like this. All the gray zones would be pegmatites or migmatitic melt material. This is almost a remelted mosh, right? So a diatexite of some sort. Well, these two rocks here have virtually the same strength. That is very, very weak compared to a rock without melt. So this photo right here showing this this melt, this little aplytic dike into an anorthosite massif, you can clearly see the shear zone being localized right where the melt is. Okay? So melt, especially in the deeper part of the crust, in the mid-crust and below, melt is a very, very important agent for strain and shear zone localization because it weakens dramatically the rock mass. Okay? So this course, as I introduced very early on, will be dealing with fault processes at depth to the surface. This is a very simple sort of schematic diagram, and I'm sure once Christy will talk about pseudotachylites, this diagram may change. But essentially, the idea with this diagram is to show that different fault rocks will form at different depths depending on the behavior of the fault zone. So very shallowly, in very shallow crustal levels, will produce incohesive fault rocks, such as fault gouge, fault powder. We'll get into cohesive brittle fault rocks and cataclasites in the deeper, slightly deeper, with pseudotachylites, which are friction melts at high strain rates. And then as we drop down, deeper down, we'll start forming mylonites, and finally in the much deeper part, very ductile component, the shear zone, straight gneiss or strip gneiss, as we call them. Okay? So different morphology of different fault rocks representing different crustal depth. Somewhat incohesive fault rocks, very hard to sample, lots of fracture planes, lots of comminution, meaning grain size reductions through milling process and crushing. This will happen at very shallow levels. As we drop down, increasing the confining pressures, we get into the world of pseudotachylites, of friction melt. This will be the zone that will nucleate earthquakes. So the seismogenic zones is usually happening between 5 and 15 kilometers depth. And as we drop down deeper, we'll form cohesive fault rocks such as mylonites, and even deeper down, straight gneisses like the diagram right here. Okay? Now, it's important to keep in mind that the transition between brittle behavior and ductile behavior is not a straight line. If we're talking about continental crust, two minerals will be very important when we describe and try to conceptualize and understand the behavior of continental crust. That's quartz and feldspar. Those two minerals are the most common mineral types in the continental crust. They dictate and control the strength of the rock. Turns out that the onset of quartz plasticity is around 325 degrees Celsius. Feldspar, on the other hand, becomes ductile at about 420 to 450 degrees Celsius. Okay? So as we move down the crust, okay, of course the crust warms up, we'll reach a point where quartz starts being ductile. Okay? So here's the onset of quartz plasticity. And then there's a zone here where quartz will be ductile, but feldspar is brittle, because we haven't yet reached the temperature of onset of ductility for feldspar until we reach, let's say, around 18 kilometers depth. It really depends on the geothermal gradient of that particular area. Okay, so this zone here will have quartz ductile, feldspar brittle. And it's only until we reach this zone here that we have a full-fledged continental crust that will be ductile completely. Okay? So we may still see some earthquakes nucleating in the quartz ductile zone, but in the feldspar brittle zone all the way down here, for example. Okay? If we're in the brittle zone and we want to deal with shear sense indicators, this is where we'll appeal to the Riedel system, for example, in the brittle fault system. So again, I'm not going to reintroduce what Riedel shears are. This should be a concept that you guys are familiar with. If not, now's the time to open up your textbook and sort of warm yourself up and get that ready. But the idea of Riedel systems in the transcurrent system, okay, so let's say we have a strike slip right here, strike slip fault zone in the brittle world. We have the shortening direction in this direction here. We'll produce secondary conjugate fault systems with opposite shear sense. One that will be synthetic, meaning same sense of shear as the overall sense of shear. Incoming call, Renaud. Move slow, move slow. Point to the screen.
Yeah.
There. Okay, hit.
Is this still coming out?
Why is it still ringing?
Content sharing.
Who is it?
Okay, we're back.
Still.
Are you guys hearing the phone ringing sound in the background?
I think it stopped.
Oh, hold up.
Okay, perfect. Okay, it just okay. We had a little episode, but we've solved it. So we're back. Okay, so back to the Riedel systems here, right? The conjugate synthetic shear will be the Riedel shear, okay? And the antithetic shear will be the R prime, okay? So these will be sort of the secondary type shears in the brittle system. There's also a synthetic low angle shear, which is the P shear right here. Okay, so these different orientations will have marked very specific slip sense, and the combination of all of these will define a Riedel system from which you can interpret the overall displacement sense of the brittle fault zone. Okay, now in the ductile world, things operate quite a bit differently. Okay, first of all, we're dealing with mylonites, which are cohesive, so that we have no sharp break in cohesion. We're dealing with mylonites, therefore we have rocks that have a very strong pervasive foliation, okay? And also a very well-developed lineation. So the two components for mylonites, right, which are rocks formed within a shear zone, a very strong planar element, which is the foliation, and a very well-defined, systematically oriented lineation. Okay, so this is essentially what's portrayed in this diagram right here. Okay, if we were to make observations of shear sense indicators, it's very important that we're looking at the correct plane, which is the sense of shear plane, which would be this surface right here. Okay, so we're standing here. Looking at this surface right here, okay, this surface here is a surface that will be perpendicular to the foliation and parallel to the lineation. Okay, the lineation is right here. Okay. There's the lineation, and the foliation is this surface right there, okay? The plane of observation to make interpretation of shear sense indicators or any other textual information for that matter must be in that orientation. So the thin sections that you'll be looking at in this week's lab and pretty much all other labs coming up are thin sections that were cut using that specific orientation, okay? If you're looking at the view right here, for example, okay, and you're looking at this surface here, you're essentially looking at the incoming train, getting bigger and bigger or smaller and smaller, depending if it's moving away or towards you, but you're not getting a sense of the displacement of that train, right? So the best way to observe a train moving is on the sides of the railroad tracks, okay? So pretend that these are the railroad tracks right here. You want to be on the side looking at the train moving from side to side. Okay, and that's the correct plane of observation. Okay. So what are we going to be looking at? If we're trying to interpret shear sense, we have a pretty sizable menu to choose from. Okay, so we'll have objects that record the sense of rotation, remembering that what we're trying to describe here when we're describing shear sense indicators is that rotational component of the finite strain axis away from the instantaneous, okay? That's the vorticity component of the shear zone, okay? So we'll have objects to choose from. We'll also have complex foliations to observe, and all these features, what makes them good shear sense indicators is they track that rotational component of finite strain axes away from instantaneous, okay? So for example, if we're dealing with what's called CS fabrics, CS, so the S stands for schistosity, and the C stands for cisaillement, French for shear, which unfortunately starts with S. The idea here is that a CS fabric here, if we're dealing with a dextral shear, okay, the strain ellipse, okay, will be oriented like this, okay? That's the instantaneous orientation for S1. That also marks the instantaneous flattening plane, okay, because shortening is happening perpendicular to that. Okay, let's do that again. Can't rest my hand on this, that's the problem. Okay, so this foliation surface, which is the S, forms instantaneously, but then as it forms, the edges of it rotates due to the vorticity component of flow. So the S flattening surface will have a sigmoidal shape, okay, as it's being sheared by the C-plane, which are shear surfaces, okay? So along one single S surface, the sigmoidal red lines on this diagram, these track the instantaneous towards the finite strain orientations. So the CS fabrics are, by definition, a very good vorticity indicator, which is why we use them as shear sense indicators. Okay? We also have another sort of anastomosing type foliation surface that's called the C prime, or extensional shear band. This surface, often called the C prime surface, is very similar to the Riedel shear in the ductile world. Meaning it's a surface that has the synthetic sense of shear as the general sense of shear of the system, okay? It is a shear plane, so it offsets locally the already developed S surface or the locally developed C surface as well. Okay, so you'll end up with a somewhat anastomosing type of fabric, and we get to use this as shear sense indicators. We'll also be using porphyroclasts and porphyroblasts. Okay? Now these are objects within the matrix of your mylonite. Either they will be strain shadow class, such as this one right here, where we have, in this case here, a pyroxene with quartz feldspar aggregate recrystallizing in what's called the strain shadow. Okay? In this case here on the right-hand side, the tails of the class are of the same composition as the class itself. This one here is a feldspar, and this is what we call a mantle porphyroclast. Now, depending on the geometry of the tails, so for example, in this case here, the tails are stair-stepping, right? They're not on the same plane. It's stair-stepping to the right, so therefore, this is a dextral shear sense indicator. The case to the right here, so this would be what's called a sigma class. Whereas this example right here, the tails are on the same plane. So they're in plane, but there is a rotational component of the clast, and it's rotating on itself and entraining the mantle with it. Okay, so in both cases here, there's a dextral rotational component, and this case here, this is what we call the delta class, okay, and both of these are recording dextral sense of shear. Okay, so again, this is a little bit of a recap of my introduction structural geology course. So of course what we'll be looking at here is either the stair-stepping geometry or how the mantle itself gets entrained into the rotating core porphyroclast. Okay. Other type of shear sense indicators which we can often see in thin sections, all sorts of mineral fish. The most common one would be a mica fish. Okay, so in this case here, in this slide here, or this slide here, we're dealing with a mica with an internal foliation. Oriented like this, parallel to the S surface, the flattening surface, whereas the C surface is oriented like this. So they're very similar as CS fabrics, but they're being developed into one single crystal. It's not just micas that do this. In this case right here, this is a monazite. So the upper case right here is a monazite with recrystallized tails that have a very similar geometry to that of a mica fish, but it's a monazite fish in this case. Okay. Finally, the other sort of more cryptic case of shear sense indicators that we can come across are what are called quarter structures. Now these quarter structures, if you just look at, we've got a central clast right here, and then we have a thin band of quartz material right here with folds being developed right here, okay? Now the idea with this case here is that this layer right here, I just highlighted in the lower quarter here, the instantaneous strain ellipse, just to remind you that lines that are oriented in the gray zone here will be lines lying in the extensional quadrant, so these lines will stretch and thin. Lines oriented in the black quadrant, conversely, will shorten, okay? So this little feature that you see right here, this fold, right, is a line that was essentially lying in the shortening quadrant of our instantaneous strain ellipse, okay? And you can also see folds develop in the other quarter, so these are strain quadrants in the shortening strain quadrants right here. Okay, so in this case here, the instantaneous strain ellipse is leaning to the right, so we are dealing with a dextral shear sense. Okay? Another type of strain quadrant would be this felspar right here. And interesting, what's happening with this felspar is you have two zones right here and right here, which are matted with micas. And what happens here is that this felspar in this zone here has undergone preferential recrystallization, has been replaced by micas. Okay? So in this case here, and the micas are oriented with this orientation right here. Okay? So in this case here, the strain quadrants are leaning in the opposite direction to the previous example. Okay? And in this case here, we're dealing with a quarter structure highlighting a sinistral sense of shear. Okay? As the shortening direction is in this direction here, maximum stretching in this direction right there. Okay? So these are called quarter structures or quarter maps in this particular case. Okay, finally, another class of shear sense indicator, which I will talk at length, I believe, next week, okay, are crystallographic preferred orientations. Now for this is not something you can readily see and interpret simply by looking at a thin section under petrographic microscope. For this, it requires the measurement of crystallographic orientations using special microscope or special imaging software. And all of this we'll talk about at length next week, but I just want to at least introduce this theme. This is a tool that is very, very useful and utilized greatly when studying shear zones and ductile fault rocks, is the measurement, the systematic measurement of crystallographic orientations within mylonites. And that can give you a lot of information, not just about shear sense, but about temperature of deformation and other environmental variables. Okay, so this brings me to the microtectonics aspect, and this is sort of, I'm kind of fusing both the end of my lecture and the start of my tutorial. And what I want to do here is very quickly go through how rocks deform microstructurally, so talk about deformation mechanisms, and then look at specific textures that you'll need to tune your eye when doing the lab the first lab assignment. Okay, and that's going to be looking at recovery textures and recrystallization textures under thin section. Okay? All right, so when we talk about microstructures, we're talking about features that are observable usually at the thin section scale. Okay, so we're dealing with thin sections or even smaller using, for example, transmission electron microscopes. We could be dealing with the measurement of crystallographic preferred orientation. We can also use different imaging techniques, SEM, scanning electron microscope, and so forth. So we're dealing with very small scale arrangement at the atomic or molecular scale, looking at geometrical elements for which we can then make interpretation of condition for deformation. Okay? Now, why do we care? Why do we want to do this? Well, if we're dealing with a shear zone, the shear zone could operate at 15 kilometers depth or 30 kilometers depth. Both are in the ductile world, but at very different temperatures and very different pressures. The rocks themselves will also have very different strengths, whether they're at 15 kilometers depth or 30 kilometers depth. Microstructures actually record all of these different deformation processes for which we can make rheological interpretations. So we'll observe things in thin section, and from that we can interpret temperature of deformation, strain rate, and how strong or weak the rock is. Everything else being equal. Okay, so there's a direct feedback, and this diagram right here sort of tries to represent this pyramid where microstructure is dependent on the rheology of the rock, is dependent on the tectonic environment, and that's essentially the temperature of deformation, the shear strain, the presence or absence of fluids. Time is a key factor as well. If we're looking at time in terms of strain rate, if we're looking at a fast-moving fault or a very slow-moving fault, that will produce very different microstructures at very different temperatures. And finally, deformation processes, what governs the generation of the microstructures that you observe in thin sections. All of these elements interplay to produce the microstructure that you observe in thin section. So the idea is to start here and then make key interpretations and inferences of deformation processes and conditions for faulting. Okay. So from a very simplistic point of view, when we're dealing with rocks and how they deform microstructurally, we have to start thinking about deformation maps. Okay, so here's a very simple deformation map. Two axes here, temperature on the x-axis, and on the y is differential stress. And these deformation maps exist for any kind of mineral, be it calcite, quartz, feldspar, pyroxenes. And these fields exist for all these different minerals. They might have different sizes and they might occur at different temperatures or stress rate or stress values, but they exist. In the lower temperature range, which is the left side of the diagram, is where we'll have the more brittle deformation mechanisms. Fracturing, cataclasis, dissolution, pressure solution, twinning, and kinking. Okay? I will be talking in the next couple of weeks about ductile deformation processes, which covers these deformation mechanisms right here. Dislocation and diffusion will be the two main processes that we'll be dealing with. Okay? The difference between grain boundary and volume diffusion, you'll notice that the boundary between these two mechanisms is a vertical line, meaning it's temperature sensitive. It's governed by a very sharp increase in temperature where volume diffusion creep can activate. Okay? The boundary between diffusion and dislocation is a bit of an oblique boundary, meaning that the change from diffusion to dislocation is temperature dependent, but also stress dependent. In fact, it's strain rate dependent greatly as well, okay, which is not portrayed on this diagram. From a very simplistic general perspective, diffusion creep, either grain boundary or volume, is a mechanism that will happen at high temperature with very minimal strain, okay? Whereas dislocation creep is a high temperature with strain. So usually during strain and heat, dislocation creep will operate. If heat persists and strain stop, you can still produce strain in the rock through diffusion, okay? Change in shape of your crystal. And for this, we need defects. Luckily, nature is not perfect. Any kind of crystal will have defects, whether point defects, which are voids or foreign atoms in our crystal lattice, portrayed in this diagram right here. We could have either linear or planar defects. These are essentially an extra half plane of atoms, or even a grain boundary in our quartz aggregate rock. All these are planar or linear defects, will be instrumental in helping the crystal to deform. Okay? A crystal without defect will be very, very strong and very hard to deform in the ductile world. We do need defects, but that's not a problem because every single crystal has them. Okay? When we're talking about diffusion, for example, diffusion is happening at high temperatures, usually in the absence of strain, and utilizes vacancies. So point defects is essential for diffusion, okay? And we'll be migrating, and I think there's a little video to kind of show this. Again, I'm having a hard time with my videos here. Works. Okay, so here's volume diffusion, where atoms are moving through the lattice through exchanging position with a vacancy. Okay, so the lower diagram is showing this green dot, which is a void, a vacancy in our crystal lattice. And as the system is undergoing a differential stress system, so sigma 1 minus sigma 3, the voids will migrate away from the crystal lattice towards the edges and eventually popping out of the crystal, and the leftover crystal lattice will be a much more stable configuration without the vacancy at all. Okay? So it's a very slow process, but with heat we can activate these atoms and they can change positions with a vacancy. And the idea here is to reduce the internal energy state of the crystal lattice by removing defects in our crystal lattice. Okay? That's utilizing diffusion. If we're in the presence of strain with heat, then this is where dislocations will tend to operate. Okay? So dislocations, of course, we need strain to activate, shear strain in this case here, and in the lower video here, what we're seeing is an extra half plane moving through the crystal lattice, breaking one bond at a time, but each time one bond gets broken, it reattaches itself as strain progresses. So we never lose full cohesion of our crystal lattice. This is in the ductile world. Yeah.
So would that be a planar defect or?
So dislocations are migration of planar defects through the crystal lattice. Absolutely. Okay? So that's what dislocations are. So you can view one as being sort of static recrystallization, static meaning in the absence of strain, but in the presence of heat, whereas dynamic recrystallization utilizes migration of dislocations, heat and strain operating at the same time. Well, we have a call. Content sharing. We're back. Okay, I have 5 more minutes. We'll take another break, and then I'll finish with the last hour. Okay, where was I going? Okay, dislocations now, we'll actually be able to see these in thin section. Namely, when we migrate dislocations, all these extra half plane, as deformation progresses, will tend to migrate and try to concentrate into a zone of our crystal. So the idea here with dynamic recrystallization is each crystal is trying to reduce its internal energy state. If it's highly disorganized with a lot of defects, the crystal will be very unstable at temperatures, at high temperatures and strain. So it will try to reorganize itself. So ondulose extinction, for example, when you're seeing that in thin section, means that your crystal lattice is bent in all sorts of different ways. Very disorganized. If you have a lot of heat and strain in the system, the quartz will then reorganize all these defects and try to lock them up into a zone, sort of a prison, if you wish. And these are called subgrade boundaries. Okay? This happens, for example, in sillimanite. So here you have subgrain boundary. This is one single sillimanite with subgrain boundaries, and each line here represents the pileup of all these dislocation planes. And in between them, you end up with subgrains that don't have any undulose extinction anymore. So the crystal kind of reorganizes itself that way. Okay? Just going to move a little bit forward here. So there is a systematic progression in organization as the crystal moves from undulose extinction, high internal energy state, very disorganized. All these little red dots represent dislocation surfaces or dislocation planes, randomly scattered throughout the volume. As we increase deformation, we increase what's called recovery. The crystal is trying to recover and reduces its internal energy state. This crystal and this crystal have the same number of dislocation imperfections in it. The difference is, here, they're all piled up into one zone. Here, same number of dislocations and imperfections, but even more organized into a very narrow zone of highly distorted crystal lattice. Okay? You can see this in thin section. And I'll give you some examples. So this would be undulose extinction. This transitional phase here will produce what's called deformation bands, and this here will produce subgrain boundaries. Okay? So in this case here, this is an example of undulose extinction. This general grain that you see right here moves from dark to pale gray zones without any very systematic way. If you look carefully at this grain in the lower left corner right here, you can see these faint lamellae. I'm not sure if the resolution on your screen shows it well. These are the start of this organization. So this crystal right here is undulose extinction, dislocations all over the volume of the grain. Here the dislocations are concentrated into these lamellae. So again, this crystal would be termed a little bit more recovered, a little bit more organized, evolved in the recrystallization stage. Okay? This is another example here of deformation lamellae, what they look like. Okay, there's a little video that shows this the stage being rotated, showing that this grain here does not have undulose extinction anymore. The extinction operates along these deformation lamellae. They're not throughout the crystal. They're kind of diffuse and transitional between one zone of the crystal to the other. This is one single crystal. That's very important to keep in mind. If things recover really well, again with heat and strain. This is an example of subgrade boundaries now, where the crystal, this is one single crystal right here, hold on. Oh dear, this is the sign of a break when things are falling apart. Okay, we're back. Okay, this is a single grain right here, okay? And the grain itself has zones of extinction. Fairly clear here, darker, darker, and then black. So the subgrain boundaries here are zones where we have a lot of pileup of dislocations. And if we were to measure the optical axis of this crystal, and I'm just going to schematically draw a line here, which would be, let's say, the orientation of the C-axis. In this zone here, it may be oriented like this. In this zone here, like this, and in this zone, like this. You'll notice that the angle is very, very small. Your eye will perceive these different gray zones as subgrain boundaries if the angle change between these optical axes is less than 15 degrees. Okay? This crystal here and this crystal here, your eye sees the boundary very sharply, okay, as a grain boundary. That means that optically, this crystal here has an optical axis greater than 15 degrees to by a quartz crystal. So your eye will see subgrain boundaries if the angle difference is subtle, within 15 degrees, or greater than 15 degrees, your eye will see it as a grain boundary. Two quartz next to each other with a sharp line, that means the optical axes are very, very different. Okay? Okay, and finally, first day with the iPad, literally. Okay, the last type of texture is a highly evolved recrystallization texture that's called chessboard texture. Very similar to subgrain boundaries, but what you see in this diagram here are very clear, very clear subgrain boundaries, almost orthogonal to each other. Okay, this is a texture that operates usually at about 620 to 650 degrees Celsius. Okay, and it's another recovery texture that is produced by dislocations being highly mobile, being very high temperature in terms of deformation. Okay. So we will do another 10-minute break here so that I can regain control of my iPad. But what I want to do in the last hour is just show you some slides of very specific textures that namely quartz produces. And these are shown on this slide here, bulging, subgrain rotation, and grain boundary migration that are very specific to temperature differences. So they're very good thermometers for deformation. These are qualitative assessment. We'll talk about quantitative thermometer next week, but this will serve as the template for what you need to observe in the thin sections for this week's lab. Okay, so I'll do this in 10 minutes, so we can all take a little break, a little water, stretch out, and convene in 10. Okay? No news, good news.
All this and more.
I'm like,
boundary migration camera.
We walk by it on our way. So like we go downstairs and then right and then out the door.
And then just around like 2 more corners and I'm like down. And
Well, no, that's on your
times.
left. Yeah, then you've gone too far.
oh, I put the Arctic Imperial.
Yeah,
It's still.
we
We walk by it.
Yeah, they would be going the other way.
Oh, that's the way.
You know?
There's only one direction. It's the top.
There's one direction.
Yeah,
Bigger, or like getting. Probably be able to get it like that. 104.
Yeah, man.
Yeah.
And it's also 2 hours.
We look
That
at
is
geotechnical
pretty
processes.
I guess otherwise that would have been very tough.
That's yeah. Really interesting. Architecture course, really interesting.
Basically
I'm serious though, let's do this. Early enough in the semester
Yeah,
that people.
that's what I was like, geez, that was like a real quick over.
Like, I'm in. I know where to get it.
I need to go back to mylographic though anyway.
Do I have to wear my?
I need to go pick up my,
Seminary yet?
Oh, yeah.
no, I just need to go like make sure that like I'm doing this thing.
But I always feel
It's like
like
still
my
working,
one true.
and then I have to go pick up my, I got to buy like a terabyte hard drive.
And the kinetic
Buy a
environment.
terabyte hard drive, we'll just record
It's like, does anyone have any strong feelings about it? If you,
Maybe I'll just
if you put a gun
I
to
have
my
to
head
Google a
and
lot of
said,
these.
Yeah, like I have no idea what is going to be the least torturous, but I'm picking that one.
Sydney, if you came back the way we lower your.
It'll also, so I will be
The
gone.
microphone.
Oh, yeah, exactly.
Everybody
Is there a
caffeine.
drinking fountain?
I really am wondering.
Okay, well, I also need caffeine.
Water's first.
the only way to keep their
Excuse you,
But right now,
my face is not long.
can you?
Yeah.
I understand it.
No, that's pretty fine.
Yeah, you're in bed.
Welcome back.
It was fine yesterday.
It'd be nice to have like a little light to know when it's on or it's muted.
Then it was really awkward. Because like
You can just
we were
yell at
hanging out, and we thought we were having a good time, then two of my roommates, their boyfriends just showed up, and then they were like watching TV, and they were like cuddling on both sides of the room, so you couldn't like leave, because they were like in the way, and the three of us were like, this is awkward, and the two of them, like the four of them, like two were there and two were there, and because we have 3 couches, and we were just like, wow, this is like the awkward couch. Like, this is a lot. I was like, you guys can go to your rooms now. We just watch this movie. Because they weren't even watching the video. Chat.
Excellent.
I was like, this is kind of awkward.
See what you're doing? Stop.
That's what my schedule looks like now. Is that you? So yeah, this is my
Okay. What's up? Together.
my sheet.
Yet again.
So that number right there, billion bytes. 34 billion bytes. That file right there is 34 gigabytes. Yeah. So like these, they all like transferred off of another system.
whatever hard drive or server.
Exactly. So I'm downloading it off the server onto Ryan's computer, and then that's just that's a RAR file. So it's basically a zip file. So I
I don't know how long
have
that
to take everything that's zipped. Sometimes there's 2 or 3 zips.
On his
You have to unzip it.
Yeah, and then put it on your computer.
I don't know. That doesn't go to the terabyte drive.
No, but
That's different. But
Yeah, but I think in
from
the
from like
I have like
I have to
on Solus and it says NG.
I'm gonna
I'm not
have
gonna get a
to
grade
change
point.
the file.
But it was bad. I think you did alright.
That's
But it was not in it.
like that hadn't been done.
You know what, man?
Yeah.
Fall portion?
No, I should have been doing the one that you did, but I was stupid and I took the proof-based bullshit.
So this is.
What did you take?
I took 120, which is the hard one.
But this one's
It's the one that you could use to transfer it in here.
Calgary would be dark by now.
120 and 110.
I know, but I know. Well, I mean, like
Color horse.
Some courses
I mean, like,
this one's.
when you know it, it's like, that's where they pulled
Like I was so confused yesterday when I woke up.
So I mean, like, a lot of it's like, yeah, do it from this principle. I'm like, you didn't explain that part.
I'm also doing
because I don't know.
like
Technically.
independent study course on top of it.
And I said, here's how you do an epsilon beta proof, and I went,
Mondays and Tuesdays. But I like Wednesday I have class at 8:30.
Shoot myself in the
knee. And then done at 3:30. And then Fridays. I'd rather have Friday. Like you can.
Are you guys in hydro too?
Like
That's gonna suck.
This is all.
No, yeah. No.
I don't know, just on like
Just
ed student.
fuck off. That's nice.
These days, they're my own class.
Which one's that?
But
466? No.
big but.
When is that? One of those?
Correct. That doesn't mean we're not necessarily the same amount of work. Yeah.
Who's teaching that?
Yeah. Although it's not, I'm actually not TAing this semester either, so that's
That's the thing.
yeah, I'm
there's
TAing
classes on
the
Wednesdays and
field
Fridays. I'm
school.
not taking it
Yeah.
because it was like
In summer,
Wednesdays
so-
and Fridays off by some weird
the
miracle.
300.
Yeah.
Oh, I'm so jealous.
Yeah.
I don't know how it happened. I was not supposed to have Wednesdays off, but
I'm actually stoked on TA.
I have an 8:30 class.
It's
Be
gonna be
great too.
And then I have an
So jealous.
oh,
And then I have.
Yeah, sure.
I'm
Yeah.
actually going back to Sun
Run away.
this weekend.
Oh, sweet.
Yeah, and we're actually staying in the exact same hotel. So when
Okay, that's what
Yeah.
but I'm gonna try to leave.
I had Gemma's class at like
Good.
what time was
See if I
it?
can
Like
get
2:30.
get
Yeah, from 2:30 to 5:30 the lab, and I got moved to
You
Friday.
can go and talk to him and be like, you can get it from him. Somebody can present it to him. I don't know. I think I'm just
I
gonna
gotta
like
figure out my
words,
hours,
like Geo18 or something.
Yeah, yeah.
I gotta figure out the easiest bioprint I can take.
Yeah.
So advanced geo.
No, like that's like.
Yeah, okay. Yeah.
That's
Yeah.
But I don't want to just get some from Mark. Get some from Mark.
Environmental science,
Yeah.
Geo 5, environmental
what was the number for that again?
science,
350. File 350.
Then you can get him, literally.
Might
Kind of loses the joke feel that way, but
I was thinking.
might take a look at that.
I think you probably not. Yeah.
The percent. I think I'll do.
bunch of
Oh,
I think I'll do.
Wait, do you need an eye clicker for that? Do you need an eye
Yeah,
clicker
no,
for
so like,
that?
it's gonna, because like we're supposed to TA like of course.
I gave my weapon.
I have one. No, I haven't taken classes.
proposing, I hope
Like they,
No, but I'm not in this class.
they say like,
It doesn't matter.
you TA this many hours, and they give you an hourly rate.
And I have
But
to
like,
No.
you know,
Right.
it's not, yeah, so like, in theory, we was only TAing like
it's so weird.
hours or so this semester, but I mean, that's benchmarking and prepping and it's.
What are they, what's the, like?
They're in geo.
Anybody else?
Yeah, like it's well, yeah, I don't know. I've never actually, obviously, I haven't done this field school, so I'm gonna figure it out as we go.
Okay.
I think I'm just pretty sure.
Yeah, just like anything.
I think
Like I just saw the changing point.
Oh no,
That's like, he definitely did it, and it's still.
yeah, coming from like like tell them like even
outside sitting here,
like in talking about your day,
It's probably on everybody.
by 4:30 we can have as much time to look at those reports.
They have us do
Yeah.
Such a huge
Yeah, I want to be like a good TA. It's actually helpful.
There is, there's a cafeteria, but it's in one of the buildings.
Which is good enough, because I'm like, no, an hour and a half.
like
Come on.
what they have to do this year is I read the entire source like just
Everyone just like, no, just like
no, that's not so. No, and then at the end they were like, yeah, and I
What the hell?
I need help with the game.
Yeah.
No. I gave him the tell him to go ahead. As north, north.
On a commencé à terre, puis on
Yeah, I don't know, like, we had a, okay, we're like actually planning on being helpful. Yes, well, you know? Yeah, though that's not, kind of.
Just to try to get a nice cost. And the guy did a little bit. Really
we don't have time to figure it out to do like
Yeah, I don't know, like definitely my favorite part of my I didn't like I had one in the Rockies, kind of like the Canmore area, and then like southwest, like kind of like the Forks area in the Dominica Belt.
I'm not really thought about that. For to be honest, now I feel right.
Yeah. Well, it's just like Lynch. Yeah, that was just like the 4th year camp in London. I did it my 3rd year.
it was always packed.
Yeah, it was.
Well, you know, it wasn't that far. But
I'm like, it's my dream.
I mean, I would love to go back and not have to do geology. You know, like it was great. I loved it. Jump in the chest, just go back because of it.
Yeah.
Okay, everyone here?
Incarceration of the bases.
I'm missing. SFU is missing one. Yeah.
It's very awkward, we get the cues from
So
the
good. Also, that guy. He's going.
Oh, yeah.
He probably is just pushing himself to the coffee.
Yeah. I'm like, I swear the number of McGill students is like diminishing every time I look up. Yeah, bro.
Miguel, are you guys ready?
Servitude to apprenticeship.
Yeah, I think so.
Which is
Yeah, we're here, we're ready.
Okay, perfect. Dan, Simon Fraser?
really weird transition.
Hey, I'm gonna take off, Laurent. Thanks, buddy.
Slacker, you're going for your 2-hour lunch, is that it?
You know, West Coast stuff. Just easy.
Okay, you're excused.
No, you're not.
But no, you're not. UFT, you guys are ready to go? Okay. Awesome. Perfect.
All 2 of you.
And you, Vic, as well? Okay. So, we've got about 45 minutes at most here, or hopefully a little bit faster. I really want to do in the next series of slides to show you very specific textural images that you will need to utilize for the first lab assignment. Okay, so we're really focusing at this point on textural evidence surrounding what this diagram is trying to summarize right here. So depending on temperature of deformation, so this diagram right here, low temperature, high temperature, and notice that there's no set values in degrees Celsius here. This is a relative textural appraisal of your textures. Low T meaning we're still in ductile though, we're not at 20 degrees Celsius. Okay, so all of these textures are at the very least 300 degrees Celsius in terms of deformation texture and deformation temperature. We're in the ductile world here. And we'll go through these one by one. And these are different ways that crystal will deform and accommodate strain at different temperatures. Okay, so bulging, subgrain rotation, and grain boundary migration. I'll illustrate a lot of these with quartz, but we could do the same exercise using feldspars. Okay, so again, those two dominant minerals that control the strength of the continental crust. So let's start with the lower temperature bulging or regime 1, and I'm using these terms because these are terms that you will see in the literature that will be posted on OnQ. The regime 1 or bulging texture is a very low temperature texture, usually around, well, again, I don't want to say a specific number here because it's dependent on other things that I'll talk about in a couple of slides. But this is the low temperature texture. And how this operates is essentially you have two grains with different dislocation densities. One grain that will have a lower density of dislocations, so a higher degree of perfection if you wish, and this grain right here on the right side, all these little squiggly lines are trying to portray a grain with a high concentration of dislocation. So therefore a very high internal energy state. Very disorganized, quite organized. As deformation progresses, there will be a local reorganization of atoms around the grain boundary, such that grains that were perhaps attached to a very disorganized crystal lattice will want to get out of there, just because it's just not organized, it's too high energy. So either they will pool up together and form a new crystal, very small, or attach themselves to the neighboring grain that has a very low dislocation density. This will produce a grain boundary that is somewhat irregular with some bulges in it. Okay? And in fact, this type of texture will see the spontaneous nucleation of new strain-free crystals right at the grain boundary. And this is exemplified by this tiny little yellow blob right here. So you have grain blue, grain yellow, two very different dislocation densities, and then you have a very, a strain-free, almost strain-free new grain, very small, right here. Okay? In real world, this is what it looks like. Okay? So imagine a sandstone that's undergoing strain, ductile strain. The sandstone will have detrital grains in it. So these are grains that were there right at the start in the primary sedimentary rock. The quartz grains will get deformed. The first thing that will happen to these quartz grains, ondulose extinction. The crystal lattice will start to distort. So you'll have very large crystals or grains, which may be original detrital grains, very disorganized because they've been there since the start of deformation, since the start of the party, right? High dislocation density, and right at the border, you'll see the nucleation of new strain-free grains. Okay, so this is typical of what's called regime 1 quartz recrystallization, or bulging, the bulging zone. Okay? It could lead to a texture that looks like this. Bimodal grain distribution, so in this case here we're dealing with a dominantly quartz mineralogy, so a quartzite or quartz arenite. The larger grains are the relic detrital grains, ondulose extinction, fairly highly distorted, and then a very small matrix of strain-free quartz. Okay? As we'll see, as we move from regime 1 to regime 2 to regime 3, as we're increasing temperature and these quartz are recrystallizing in the presence of heat and strain, the grain size will progressively increase. Okay, but initially we're recrystallizing it, producing strain-free small grains in the bulging or regime 1 zone. Okay? Now, as we undergo more strain and more heat in the system, if heat is available, we'll start moving those dislocations into subgrain boundaries, just as we saw and illustrated with the seliminite grains before the break. If we pile up enough of these dislocation extra half planes, okay, and in this case here, these blue lines here represent the crystal orientation, or the C-axis in the quartz. You'll notice here that this is one single quartz grain where different zones have very subtle angular differences with the crystal lattice of neighboring subgrains. Smaller than 15 degrees. So your eye will perceive these lines here not as sharp lines, but as diffuse subgrain boundaries. Okay? If you have more and more subgrain rotation going due to pileup of subgrain boundaries, let's say along this subgrain boundary may at one point rotate beyond the 15 degrees difference with the neighboring subgrain crystallographic orientation. So at this point here, your eye will perceive this not as a diffuse subgrain boundary, but as a grain boundary itself. It becomes a new grain. Okay? Now, what it will look like in thin section will be something like this. Okay? Where you have a fairly homogeneous grain size. Okay, if you look at this mass here. And then if you're trying to focus on the grain or the different grayscale on this thin section, let's say you're moving from here to here to here. The grain boundaries are somewhat diffuse and not sharp. These are subgrain boundaries, meaning that the optical orientation of the crystal lattice between here and here, or here, is within 15 degrees. But if you go from here to here, there's a very sharp black line. That's what your eye sees. That's a grain boundary now, meaning that this little grain here has undergone subgrain recrystallization, or subgrain rotation recrystallization. Okay? This is what's called regime 2, slightly higher temperature for dynamic recrystallization. Okay? So gradual transition from subgrain to grain boundary. You may have still some relic large detrital grains with undulose extinction. And keeping in mind that these are all transitional state. So you may have a thin section where you have bulging textures and subgrain rotation recrystallization in the same thin section. You're right in that transition. Okay? But this tells you that this thin section, or this rock, everything else being equal, has deformed at a slightly higher temperature than the previous example. Okay? In the ultimate state of subgrain rotation recrystallization, you may have a texture that looks something like this. Okay? Fairly uniform grain size distribution. And again, some zones here, if you look at this zone right here, the boundary between the different grayscales is not sharply defined. It's diffuse. Those are subgrain boundaries. Others, you see very sharp black lines. Those are grain boundaries. Okay? So that tells you that you've got a mixture of subgrains and grain boundaries. What's interesting in this texture as well is that your quartz crystals, your quartz zones, define what's called a grain shape preferred orientation. Your quartz tend to have this orientation. So although this rock does not have micas, silicates to define the foliation, this is a quartzite, you still have the presence of a foliation, a flattening surface, a grain-shaped foliation defined by the recrystallized quartz grains in this, okay? Slightly higher temperature texture than the bulging texture of regime 1. Okay? At much higher temperature, then we get to a more extreme case of bulging. This is called grain boundary migration. And this is where diffusion starts to really assist dislocation in terms of deformation process. Okay? So the bottom line texture, what this will produce are highly serrated grain boundaries. And I'm just going to draw here one grain boundary here. You'll see that it's very irregular, almost looks like an amoeba. Okay? So this grain boundary, highly serrated, is evidence for grain boundary migration. And the way this works here is you have, let's say, crystal A and crystal B. Okay? And with heat and diffusion, the atoms in crystal lattice B, which is highly distorted, for example, instead of keeping their attachment to the crystal B, they will break their bond with the crystal lattice that's disorganized and attach themselves to the neighboring, more organized quartz grain. This produces a texture in which the quartz grains with fewer density of dislocation will grow at the detriment of disorganized grains. Okay?
How is that different from bulging?
Bulging is very localized just on the grain boundary and will produce new growth, new crystals. So if you look at the texture here, this is grain boundary migration, so it operates along the entire grain boundary. Bulging, what it would do are little new grains right at the grain boundary instead. Okay? So, Renaud?
Yeah, one thing I would add is that bulging is usually really, really small scale compared to grain boundary migration. So with bulging, you'll have extremely small bulges compared to the original grain. It's like 2, 3 order of magnitude smaller, whereas with the grain boundary migration, they're not that small compared to the...
So grain boundary migration will involve a fairly large grain, keeping in mind that also grain size, as we go from regime 1 to regime 2 to regime 3, grain size increases because we're at higher temperature and we're producing, the dynamic recrystallization will produce much larger crystals through deformation and metamorphism, okay? And grain boundary migration really involves all the grain boundaries. Good question, okay? So in this particular process, diffusion becomes activated also. That's the other difference, right? In subgrain, in bulging, which is a lower temperature, is mostly dislocation. Here, the atoms are in fact changing their bond attachment from one crystal that's highly disorganized, breaking that bond, reattaching themselves to a more organized, dislocation-free grain, okay? So in this case here, this grain here would be grain A with a much lower dislocation density than grain B here, and this grain here is bulging into that grain and growing at the expense of more disorganized grains nearby. Okay? So this diagram on the left here, okay, shows really the textural difference between bulging and grain boundary migration. All these grain boundaries in red, right, highly serrated grain boundaries, fairly large grain, typical of a high temperature regime 3 fabric. Okay? So just by looking at 3 different thin sections, quartz dominated mineralogy, looking at these 3 textures, you can actually position one at much higher temperature of deformation than the other, in the absence of any other thermobarometry or metamorphic mineral index, just by looking at quartz textures. Okay? Finally, there is one other texture that will operate with diffusion, but in the absence of strain. Okay? This is called G-bar, or grain boundary area reduction. This is the beer foam texture, right? So if you have a grain, let's say, that shows beautiful grain boundary migration texture, such as this, high temperature deformation fabric that's produced by heat and strain. If the heat persists in the absence of strain, notice how these grain boundaries become much straighter, and the grains then joined up in triple point stable configuration. Okay? This is called static recrystallization, and it occurs in pretty much any kind of mineral if you have sufficient heat to activate diffusion process without deformation. So dislocations are not migrating through the crystal lattice. You're in fact reducing the internal energy state of your crystal by bringing the grain boundaries in a stable 120-degree configuration. Okay? So if you pour your beer really fast in a glass and take your hand lens and look at the foam, you'll see these bubbles forming in much larger with time. That's a perfect example of essentially reconfiguring your bubbles in your beer foam into a stable 120-degree configuration. Your foam and your bubbles will eventually look like this if you let your beer settle and not drink it too fast. Okay? So these are scapulates, so these are not quartz, just to show you an example of other minerals. Beautiful triple point junction, for example, right here, all these crystals are joining into beautiful 120-degree grain boundary here, so forth here. So this shows me that this grain here, or this crystal mass, has undergone static recrystallization, grain boundary area reduction, meaning heat was available in the system without the presence of strain to essentially reset the fabric and ready for the next increment of deformation after. Okay, so this is a way for crystal for rocks essentially to heal from deformation if heat is still available. Okay. Keeping in mind that if you have, let's say, a coastal feldspathic rock with quartz veins in it, the degree in which these quartz will recrystallize statically and produce this G-bar texture or foam texture will be controlled by the width of those quartz veins per se. So here we have, on the left side, very thin quartz veins, and here, a very thick quartz vein. So the quartz crystals, as they're undergoing static recrystallization, in this case here, will have the space to form very nice triple point junctions. Whereas in these very thin quartz veins here, you just don't have that space. Okay? So be wary also of the size of the sample that you're looking at and the availability for crystal to grow in terms of size and texture recorded. Okay. Now here's the beauty of all of this, especially if we're dealing with feldspar and quartz, the two most common minerals in the continental crust. Bulging, subgrain rotation, recrystallization, and grain boundary migration occur in very different temperature settings. Okay? Feldspars at much higher temperatures, okay, there's the temperature axis right here, Bulging around 350, subgrain recrystallization around 400 degrees for quartz, and about 500 for grain boundary migration. And of course in feldspar, the brittle to ductile, which is this boundary right here, occurs at much higher temperature, but then the bulging, subgrain, rotation, recrystallization, and grain boundary migration occur at higher temperature. So we can use these textures as relative proxy for temperature of deformation. Okay? Now, there's a couple of caveats or things that we have to think about and worry about. One is the influence of pressure in the system. Okay? These boundaries here, for example here, yes, they are depicted as being primarily controlled by temperature, but we could draw this for pressure as well. Pressure will be an influence in the transition between regime 1, regime 2, regime 3. I've talked briefly about chessboard texture, which is this texture right here, okay? Meaning a texture that produces highly mobile dislocation surfaces. These are subgrain boundaries operating in orthogonal direction, usually occurring at about 620 to 650 degrees Celsius and beyond. This is the kind of texture you see in migmatitic rocks. The boundary between chessboard texture and regular grain boundary migration, this line is not a straight line. It actually varies as a function of pressure. Also very important is the strain rate. Okay, so here's a diagram here showing the different textures: bulging, subgrain rotation, grain boundary migration. You can clearly see the difference that Renaud was pointing out, this very small grain nature of the bulging versus the grain boundary migration serrated boundaries. And on the right is a diagram showing temperature of deformation on this axis and strain rate increasing in the y direction. Okay? And with the three zones: bulging, subgrain rotation, grain boundary migration. You'll notice that, for example, bulging at very slow strain rate, okay, let's say at 300 degrees, can happen here at 10 to the minus 14. At high strain rate, it could happen at very high temperature. Okay? So, strain rate is very important in governing or influencing where these or how these textures can develop. Now, luckily, geology tends to operate, and shear zones, ductile shear zones, tend to operate in these strain rate ranges around here. Okay? Between 10 to the minus 10, 11 to 10 to the minus 14. Okay? This is the real world. Okay? Very fast shear zones, 10 to the minus 10, 10 to the minus 11. Smaller, these are tectonic velocities, 10 to the minus 14. Okay? Which are the strain rates that are usually inferred when trying to interpret the temperature of deformation with these textures. Okay? But does not say that, for example, in these diagrams, it showed the difference between two systems, the Alpine Fault zone and the Ruby Gap duplex. Two shear zones operating at different strain rates will produce this transition between bulging, subgrain rotation, and grain boundary migration at different temperatures. Okay? So when you're writing a report, for example, and hint, like the report that you will produce, you do have to state your assumptions. I interpret this texture to represent 375 degrees, assuming a strain rate of, okay? Because that's an assumption that you won't be able to verify in the lab, but you do have to think about when you're interpreting a texture. Okay? So this brings me to this week's lab. Okay? So what you will have a series of thin sections coming from New Zealand. Now I have to say right away, for our remote colleagues, Those thin sections will be on your way tomorrow. We're going to ship them out through Perlator tomorrow morning. So you will get them within a day, but unfortunately you won't have them for tomorrow, but you'll be able to work on them as of Wednesday. Hopefully you'll have access to microscopes for this lab. You guys are all good for that? Thumbs up? Yes? Thumbs up or sort of a maybe? I can see. So you'll have all, except the UVic, sorry. You won't have them. And they're coming from the Alpine Fault. So what I want to do here is very, very briefly, this is a New Zealand Geology for Dummies, just introduce you to the context of New Zealand. And then I'll go very quickly on what the lab actually entails. So New Zealand sits at a very interesting position. It's actually a plate boundary between the Pacific plate and the Australian plate. And the plate boundary is right here and goes right through the South Island of New Zealand right here. So the North Island of New Zealand is in fact sitting on the Australian plate, and on the South Island, most of it, at least the southern part of the island, lies on the Pacific plate, and it's only the northwestern tip that lies in the Australian plate. Okay? So part of this plate boundary is on continental crust, and this plate boundary is called the South Alpine Fault. Okay? Now, one thing we tend to forget is that New Zealand and the South Alpine Fault actually marks a continent-continent collision. Okay, so on this map here, what you're showing in brown are continental crust. Okay, most of the Australian plate, and between New Zealand and Australia, there's an ocean. But underneath the water level, part of it is oceanic crust, depicted in blue, and the brown is actually continental crust. So there's two continental fragments, one on the Australian plate, one on the Pacific plate, and they're both joined and colliding. And that's why here we don't have subduction system, because we have two continental crusts which are buoyant, that are locking up and forming a strike-slip boundary mostly, with a little bit of a reverse sense. Okay? The North Island is continental crust on one side and an oceanic plateau on the other side, whereas the southern tip of New Zealand right here, we in fact have ocean crust colliding, and one of which is subducting. Okay? So if we zoom in now to the South Island, where we have continent crust colliding, it's mostly a strike-slip dextral fault, but there's also a reverse sense fault. Okay, so here's the a profile of the island right here. So there's South Island. This cross section here, sort of like this, west, east. Okay, so there's the Australian plate on the left side and the Pacific plate on the east side. The area elevated here are the Southern Alps, Mount Cook being the highest point here. So all of these high ranges on the South Island are mountains developed on the Pacific side, on the Pacific plate. Okay? Because the South Alpine Fault is a mostly strike-slip fault, so it's moving dextrally, so it's dot there and an X here. It's also a reverse fault. Okay. And the interesting part about that reverse fault, it brings deep material to the surface. Okay. So if you were to walk across South Island from this point here towards the Alpine Fault, metamorphic grade will increase as you get closer and closer to the plate boundary, because that plate boundary has a thrust sense Pacific plate over Australian plate motion. Okay, so there's an increase, and these colors here are showing the different metamorphic grade And as you get to the base of this, you're getting into upper amphibolite facies metamorphism. Okay, so much higher temperature as you get closer to the fault zone. Okay, and all of this in the Southern Alps, all these rocks are ductily deformed. Okay, give you some field shots of this plate boundary. This is my wife here looking unimpressed by the plate boundary between the Australian and the Pacific plate. I'm just going to draw it here so that you guys can see it better. Plate boundary is actually right there. Okay, this here in the background is the Pacific plate. That's slightly higher, and then there's a topographic break. And on this side is the Australian plate. Okay, there's the reverse fault right there. Okay, this is not the entire reverse fault. This is just the active fault scarp of the thrust fault because it's a seismically active deforming plate boundary. Okay, there's even a little sag pond right there. Okay, so this zone here is moving down, this zone here is moving up. Okay, and there's also, which we can't see on this diagram, a dextral, component. Okay, so that's the active fault scarp, and of course, you know, there's no rocks here. This is in the alluvial plain in the Haast River zone. Things got a little bit more spectacular in different areas. So this is all along the west side of South Island. This is Harry Mary Creek. And in this area, it gets a little bit more exciting. We have alluvial, unconsolidated gravel here. All of these, right? And in the upper part here, sort of an oblique zone here, these are amphibolite facies mylonites, overriding unconsolidated gravel. Okay, that's the active thrust fault. Okay, we also have very nice mylonites. This is at the base of Franz Josef Glacier, and if you look at the mylonites, and you'll have samples of this to look at. If you look at, this is a vertical face right here. If you look carefully on the foliation surface right there, you could possibly see the subhorizontal lineation. Okay. These are quartz rods recording this strike slip component of the fault zone. Okay.
Could you use a bit brighter colors? It's hard to see the orange.
Okay, absolutely. How about I use green? That's terrible.
Hey,
that's it.
Better.
Red, okay, that's on the foliation surface, okay? So this is just to show you the different rock types and different setting for this Alpine Fault. The plate boundary is pretty spectacular because, you know, I'm sitting here at sea level, and there's glaciers coming down pretty much at sea level in a tropical rainforest, and all the background there is the Pacific plate, okay, and I'm sitting on the Australian plate, okay. All right, one of the possibly the most spectacular sites to see the Alpine Fault is called Gaunt Creek. And Gaunt Creek, okay, this is a picture of Gaunt Creek right there. There's the thrust fault right there. Okay. These gravels in the foreground have been dated, and they're 12,000 years old. Okay. The rocks right here are amphibolite facies rocks that were deformed at 20 kilometers depth. And they're overriding virtually undeformed, unconsolidated gravel. And the thrust surface is right there, slightly altered amphibolites right here, and these are the gravels that the Pacific plate is overriding. So here's the plate boundary, that's Pacific plate, and this is Australian plate, right there. Okay? Okay, to the mission now. Okay? I've collected a suite of samples, okay, at all these different sites. Okay? There's a number of specimens for each of these, with thin sections associated with all of these, and they've all been mixed up. Okay? So, the idea here is for you to describe, I think there's 10 thin sections to describe, and each of these belong to different locations. So you will have to describe these thin sections looking at relative temperature of deformation. Of course, the higher temperature deformation textures should be found closer to the fault and lower temperature away from the fault. Closer to the fault should also have a higher degree of strain, away from the fault, lower degree. So you should be able to document a strain gradient from far away to closer, okay? And also an increase in temperature as you get into the shear zone until you drop into the footwall and then you're in low temperature, okay? So for this, okay, so there's a couple of things. You need to describe as completely as possible all the thin sections, so that will require some sketching and some description using all the different criteria that I've talked about today. You'll have to locate and reorder those samples in the appropriate sites. What we're doing is we're providing you with bibliography, so papers that you can download on the Queen's Library, and also some field trip reports that are posted on OnQ, in which they describe the different textures at the different sites. Okay? So you have to do your own description, and then you have to read those papers and look for similarities and say, well, what I've described looks very similarly to what Pryor described at Concrete, for example, in this paper in 1987. Or it's somewhat different to that. So you'll have to do some reading, some lit review, and your own description, and then present a clear and concise interpretation for all of this. Okay, and this will be done in a formal lab report. On OnQ, in the lab assignment file, Renaud prepared also a marking scheme, things that he expects you to do in terms of presentation, in terms of where the weight of the marks will be distributed. We do expect a professional looking report. You have 2 weeks to do this, starting tomorrow for the Queen students. You have your lab time at 2:30 tomorrow in Miller 3-9. In the microscope lab. There you go. And for McGill, U of T, and Simon Fraser, your samples will be sent tomorrow. Unfortunately, our technician was still cutting. You've got a call. Okay, so yes, unfortunately, U of T, McGill, Simon Fraser, our technician, was still finishing up the thin sections. Christmas break didn't help, but they should be all done by tomorrow morning. We'll send them to you as soon as possible, and then you can start working on those samples. I also have a bibliography here that I've just posted, but that's also in your lab assignment handout. We will be posting also a couple of field trip reports that you can download and read. Some of these papers, if they're available on the library, all of these in fact are, then it's up to you to use the library skills and go and download these and then read them and then hunt for their description and try to match their description with yours and reposition all those samples in the right place. Okay? Yep.
Are these individual?
Okay, so the way we work, lab reports in teams of 2. Okay, we have 15 microscopes for 15 teams. We've got 30 students at least registered. Don't see 30 students here. Teams of 2, yeah, you've got 2 weeks. So tomorrow we'll be there. Usually we tend to be there in the lab for the first week, and then the second week it's up to you guys to do the work. So we expect you guys to be a lot more independent in those type of reports. All of these labs throughout the term are using real-world examples, real-world samples, and we're trying to really have you guys work on techniques that are real as opposed to fake examples that we do in 321. Yep.
Samples be out after the lab or?
Yeah. So the samples will be available for 2 weeks in the lab. You guys can, of course, show up for the first lab to, we'll be there to answer questions, but you're more than welcome to come off hours and do your own work as well in the next 2 weeks. Okay? Are there any questions from McGill, U of T, UVic?
There's a few of us here who we don't have access to OnQ yet, so I'll send you some of those email addresses.
Oh, some of you are not registered yet?
Yeah, including me. This is Kristen.
I saw your name, Christy, on the OnQ, so you should be able to log in.
I haven't received any email about it, so I don't know how to log in.
Did I sent you an email with your temporary password, right?
No.
Okay, none of the McGill people have received email?
Some people have.
Okay. Well, I'll check my emails and make sure that I'll resend all that information. But
Okay,
from my side, everyone who has sent me an email should have been listed on OnQ, and you guys, I see you from my end. I'll just make sure you guys all have that information.
Okay, thanks, Laura. I also have a couple of new people to add, so I'll send you an email.
Yes, those new names will just take maybe a week before the system, because the IT people have to do that from our side. And of course, it's the start of term and it's all slow. But you can share resources.
Yeah, we'll share amongst ourselves here.
Okay, perfect. Lindsay, U of T, you guys are good? Oh, incoming call. Yeah. U of T, you guys have received the OnQ connection. Does it work?
Yes.
Yes? Okay,
Yes.
Simon Fraser? Hello. There's a mute button in front of you. I just want to know, thumbs up if you guys got the OnQ information. Yes.
Yeah.
Did you get the OnQ?
Yeah, we have. Thank you.
All right, okay. Okay, guys, thank you very much. I know the first week is always very awkward. It's the Skype gone way out of control, but hopefully as the weeks progress, we'll get better at it as instructors and also for you guys who get more comfortable. Okay, that's it. Thank you very much, everyone.